So let's have a look at this. So minus ls just shows the listing of the folder. When you say Hadoop fs minus ls, it just shows the listing of the folder. Okay. So this output 4 was created, and this is where the data is. Okay. To see what's there in the file, you can use Hadoop fs cat, and cat gives the list of the values. Okay, in the file, whatever is there in the file, it just prints to the screen. Okay. All right. So this was something which I do not expect you to learn right away. In case you did not understand, do not worry. So we tried to execute Hadoop jar like this, and then executed the cat file to see what's there. Okay. And now back here. All right. Any questions here? So yeah, Nitika, is it okay now, or is it still badly breaking? All right, because I hear I have two connections, and both of them is having this problem of connectivity. Yeah. All right. So this is still better than the other one. Okay. So let's try if we can get along with this minor glitches, and if not, then we'll have to figure out what needs to be done. All right. So we generally talked about how to create file, how to see upload file into HDFS, general overview about how to execute, how does Hadoop works. Now let's start this exercise where we will gradually move into thinking in terms of MapReduce. Why does it make sense to have MapReduce kind of thing in place? Okay. So let's take that in your company, if your boss asks you that here is a big text file, and what you need to do is give me the frequency of unique words. How many times each of the words have occurred in this big text file? Okay. And this text file, you can imagine that it's all of the Lord of the Rings book in plain text format. All you need to do is count how many times each word has occurred in this file. Okay. Or you can say the number of times each unique word in this file has occurred. That's what you have to count. Okay. So this is a general task. If your boss or your professor asks you to do it immediately as a real work, what is it that you're going to do? It's not a trick question. It's a general question of day-to-day life. So what is the approach do you take? Nitika says use unique command of Unix. But before unique, could you write down the command? That will be better, because what is the assumptions for the unique command? Yes, anybody else? If you have a big plain text word and you have to count the number of times each unique word has occurred in this file. Okay, so let me just take some example, and I say, okay, so let's for just example sake, let's say this is the text I'm having, this is the text I'm having, and all I want is I want to find out the unique words in it. Okay, unique word and their frequencies. So anybody else who can, other than Nitika, how would they do it? What tools will you use? Will you use Unix? Will you use databases? What the approach? So whatever you think is, you know, a general, a big on a you know, at a very macro level, what is it that you're going to do? Anybody else? Harshal says use Excel. Good. Nitika says you by SQL command. Okay, good. And what else will you use? It's a probably, I'm assuming that Pop says use count command. So count command of SQL. Okay. Vikas says through string tokenizer. Okay, go ahead, go ahead. I'm looking for that kind of approach also. Good. Vikas says use R. Goyal. Goyal says use R. Misha says will split and count. Split in terms of what? Split on basis of what? Okay, so you will use string tokenizer, and after that, what will you do? String tokenizer is nothing but converting the text file into a big. You can imagine that it converts it into a big array of words. Now, after that, what will be your approach? Anybody else? Any general strategy? So it's a day-to-day task, because if you are an IT company, from time to time you might have to churn the information into various forms. Okay, and sometimes this kind of job you might also get. Malvika and Amar says that write a program to read the file, tokenize the input, store it in db as word count, increment count each time the word is encountered. Okay, so okay, good, good approaches. In Java, use simple hash map. Okay, that is Vinay. Hash map. If text file fits into RAM, good, excellent, excellent. Nitika says you can write code in PHP or any other programming language. All right, all right, all right. I understand, yes. So I'm not looking for map reduce right away. I'm looking for all possible approaches, and we will understand their drawbacks before jumping into MapReduce. All right. All right. So A general approach is a good idea. Sweta says put all the words in a set. For each word key, maintain a hash map and increment the count each time, each true or false. Excellent, excellent. Okay, great, great, Vinay. So, all right, all right, good, good. Thank you, Vinay. And I'm assuming it's Vinay, right? VN, Vinay Nandi. All right, good. So here we are. We have got a great approaches from all of you. So this is what you have. The other approaches we will take in the second slide, but let's analyze this approach. Okay. So we create a frequency table. It could be a hash table or a dictionary. If you use Java, you generally call it a hash table. If you use Python, you generally call it a dictionary. And it's nothing but a key value pair, a collection of key value pairs where you can immediately look up for a word and it will give you its value. Okay, and it's really really fast. A frequency hash table is extremely fast. It's like an array where the instead of index you have this word, instead of a number you are using a string as an index. All right, so you can imagine a hash table that way. Oh, okay, so let me reiterate again. So the general idea is to create a dictionary. Okay, general idea is to create a dictionary. Dictionary is also called a hash table or a hash. There are multiple data structures to represent a dictionary. Okay, all right. So you create a dictionary. For each word in the file, you keep on adding to the dictionary. If it already exists in the dictionary, increment the count. If it does not exist in the dictionary, you add it in the dictionary. All right? Hello. Hello, can you hear me? Yeah. Actually, my both the net connections are giving trouble, and that is probably the reason why the replication factor is generally kept 3. Okay. So probably I'll have to buy one more backup. Okay. All right. All right. Let's try to manage with it a little bit more in case. Yeah. So the problem is that it has rained heavily, and that is the reason why most of these connections are giving trouble. And yeah, of course, we can't blame the earthquake for this, probably. All right. Yeah. So we were talking about a dictionary. A dictionary is basically a key value pair collection of key value pairs, and in programming terms, it's a very frequent data structure. And a dictionary is generally in the memory. Okay. So for each word in the file, we figure out whether we have already added in the dictionary or not. If not, we add it into the dictionary, and the value in the dictionary, key in the dictionary is the word, and the value in the dictionary is count how many times a word has occurred. So if the word does not exist for the first time in the dictionary, we add it with the count as 1, and as and when we encounter the same words again, we just increase the count instead of adding it again. All right. So that's the dictionary. And and when we have no longer any, the end of the file has reached, we print out the whole thing, what is accumulated in the dictionary. Okay. So do you think that this approach is correct? And what are the faults with this approach? Good. That's good. Harshal says that what if the file size is big? So the answer is no. Yeah, that is very correct. Goyal is says doesn't seem to be too lengthy. Okay, okay. Time consuming. Nalini says time consuming. Okay. So this is not manual. We are going to do it programmatically. Good. Malvika says it's not scalable. Excellent. What if file size is in GB? Then answer is no. Good. Very good. All right. So you have already answered. So we can move on to we cannot process the data that does not fit into the RAM. All right. And a hash table, generally, if you're using a Python hash table, the amount of memory it takes is around 4 times the file size. Okay. All right. What about Java? Java also takes around 2x times the actual data, or maybe more. Okay. All right. Now the second approach, some of you came up with this nice approach of using SQL. Break the book, the whole plain text into one word per line, then insert this into table and then execute this. Select word and count star from the table, group by the word, right? Sounds good to you? Is this approach clear to all of you? All right. So what are the problems with this approach? Okay. Nitika says it's a heavy query. All right. All right. Let's see one more approach. Okay. Size of DB constraint. Good. That's thank you, Vinay. So now let's look at the another approach. So another approach is via Unix, where we replace space with a new line. Then, which means, what does it mean? Replacing the space with a new line. Basically, we are converting the file into one word per line. All right, we are converting the file into one word per line, and then the order these words using a sort command. And after you have ordered these words using sort command, then find the frequencies using unique. Okay. Now, please note that this unique is essentially unique only works on the data which is already ordered, which is already sorted. Okay. It basically scans from the top to bottom and prints the count whenever the value changes. Okay, so you can see that we are doing cat file1, file2 and so on, all the file concatenated together. We are printing it as a pipeline to another command, this command, and then we are pipelining that to another command. Okay, and then we are pipelining it to another command. All right. So I'm hoping you understand. So in Unix, you can basically feed the output of one command to as an input to another command. So this is one command. Cat is one command. All it does is concatenates file 1, file 2, file 3 and so on and gives out the output. If we only execute this cat command, then it will print out everything onto the screen. Okay, you can read through it. Now, in case you put a pipe and feed this to another command, then this data of cat becomes the input. The output of cat becomes the input to this command. And what does this command do? It substitutes it substitutes the space, which is space or tab, many of those with a new line. All right. And after that, the output of that is fed to the sort command, right? Now notice this minus s1g. What does it say? Sort using only 1 GB of memory. So there is no way it can overflow the RAM, right? And then count the unique. Now with approach number 2 and 3. Okay, one approach is Unix, other approach is using SQL. Both approaches are very similar to each other. Okay, so what is it that you see the problem with? What are the problems with the approach number 2 and approach number 3? I'll answer your question also now, Ajay. Ajay's question is, I have a question with respect to OLAP data warehousing. Doesn't it have the capability to run the previous SQL query? It does have the capability to run the SQL query, but there are minor glitches. We need to talk about those. Okay. So when the data keeps growing, do you think the approach 2, which is SQL, and approach 3, which is Unix command, does it have any repercussions? Anyone? What are the problems will you face in these two approaches? Excellent. Excellent. Vinay says if the file size is beyond your hard disk, it would not work. That is also true for approach 2, right? Good. Ajay says that not sure about petabyte, but terabyte data can be handled by Teradata DB. Okay. All right. Good. So the general problem you will face is the moment the data starts going beyond RAM, the time taken starts increasing. Okay. And why? Because both these approaches, whether SQL or Unix, both of them internally are sorting the data. And to sort the data which does not fit into the RAM, you will have to create the sorted data sets. You have to divide the data set internally and sort them partially and then combine them together. Both SQL as well as Unix will be doing the same thing internally using different techniques. Okay, and the moment the data grows beyond RAM, meaning if your data is beyond, say, 2 GB, which means parts have to be created onto the disk, the data has to be written onto the disk again and again, and the disk speed, disk space, and the CPU will become the bottleneck in this. All right? Yeah. Harshal, you are right in that. So RAM will not be a problem in this. Because of RAM, we tried to avoid these both these approach will try to avoid the RAM becoming the bottleneck and making disk space and disk speed and CPU as the bottleneck. Isn't that right? That's right, right? Is everyone with me? If you have any doubt, feel free to ask. I would be more happy to explain you again. Okay. Our input is in more than one file. Okay. Yeah. So basically here there is a minor syntax difference. Although we have already said that we have only single file, still we have put more than one file. So you can simply say file one. Okay. All right. Good point. Good catch. Now let's move ahead. Now let's talk about a fourth approach. In this fourth approach, what we are going to use is an external sort. What does it mean by external sort? We have multiple machines, say machine 1, machine 2, and so on. Now, in this approach, what we do is we split our big file into small files that can fit into the RAM. And once we have done that, we send that chunk to we send that small file chunk to each individual machines and get them let them use the approach number one, which is creating a dictionary, and do the counting. And once they are done, once a machine is done churning a small data, let it send the the sorted output, or the output from each machine back to the place from where the process is started. We call it a launcher. Okay. So again, let me reiterate the process. So what we are trying to do here is from launcher, we are splitting the file into two parts. First part goes to machine 1, second part goes to machine 2. If you have more machine, you can also send them to other ones also. And then let each machine let each machine reply let each machine reply with word counts, okay, in an ordered manner. Afterwards, this launcher will merge the outputs together and give you the results. Make sense? Imagine that from launcher we had a file containing SAR array in one line and second line containing this. First line was sent to machine 1, second line was sent to machine 2. I'm taking one line an example just so that it's easy to explain. Okay, ideally this data which we are sending to machine 1 will be maybe equal to the RAM size, or maybe half of the RAM size. Okay, and we send it to machine 1 and machine 2 and let them sort and get back, and then after they have given their results in a ordered manner, we can merge the results and give the output. Does it make sense to you? Does this approach make sense to you? All right. And some of you may not be aware of the sort command, sort minus m. Basically, it merges two sorted datas. All right. Now, this is one approach. Now, although this sounds like a brilliant approach, but do you still see some problems with this approach? Anyone? Okay. Nitika says it's lengthy. All right. Distributing data. Yes. Common definitions. I need to understand this point, Sanjay. If you could elaborate. Excellent. Vinay says, what if one machine fails? Right? So you'll have to plan all of those kind of, worst case scenarios. Good. Sweta says, what if the merged data is too big? Meaning the merging process itself is too heavy. What would we do then? Good. Good. Yeah. So Sanjay's point is each machine able to define the data the same way when it comes out from the launcher? It's a good point. I'll tell you exactly why this point is very valid. All right. So one thing is very clear from all this discussion, that it definitely requires a lot of engineering. Okay, it definitely requires lot of engineering. Sanjay says that you'll have to have the same, the data uniformity from machine 1, machine 2, and launcher. And then Sweta says that what if the data is too big? Again, the launcher need to divide the data, or how will launcher handle if the data is really too big to merge? What if machine fails? All right. So all of this, and distributing data, that is another problem which Ajay has pointed it out. All right. So now all of this can be summarized in a single sentence, that is too much of engineering involved. Any other point do you have in mind? Distributing data is one big point. Why? Launcher has to send this data every time to machine 1 or machine 2 or machine 3 and so on. What if our data was already divided in blocks and is already on machine 1 and machine 2? We could take the benefit of that one. All right? We don't have to transfer the data. And that's exactly the purpose of MapReduce. All right. So time is consumed in transportation of the data, and trust me, the time is really, really huge. Not only transportation, but reading from the disk and writing to another disk will take time. All right. And for each requirement, you have to keep on programming again and again. And this whole machinery requires a lot of engineering. So the solution to all of this is MapReduce. All right. So we talked about four approaches so far. First approach was using a normal program where we keep on preparing it into the memory, a dictionary. And then second approach was using SQL. Third approach was using Unix. And fourth approach was using external sort. All right. And fifth approach is using MapReduce. All right. And you will be surprised, this approach is partially what we will discuss when we talk about Apache Spark, the approach number 4. All right. So is everyone with me? All right. So before we take a break at 9:30, let me just describe you what does it mean by MapReduce. A MapReduce is a programming paradigm that helps you solve big data problems, such specifically those problems which are sorting intensive. You will have to code two functions. One is called mapper, other is called reducer. Okay. While the mapper converts the input into key value pairs, reducer aggregates all the values for each distinct key. Okay. For each distinct key, reducer aggregates the value. So you will have to write the reducer. You will get a list of values for a key. How to combine, that's what you will write in the reducer code. In Mapper, you will convert the input data. The input data could be in XML. The input data could be in plain text. Input data could be in binary. So the role of the mapper is converting this data into into something which can be sorted, you will have to give key value pairs. All right. It's not specific to to Hadoop. Other people, other databases such as MongoDB, CouchDB, and Cassandra, along with Apache Spark, all have accepted the MapReduce paradigm as the core, as their core processing engine, as the core processing paradigm. All right. And mapper and reducers can be written in Java, Shell, Python, or any binary. The existing binary also you could utilize the as mapper and reducer. All right. We'll go into the details after the break. All right. Let's take a break of 5 minutes. Hi, can we start now? Huda, can we start now? Are you back? I think she's not back. All right. Yeah. So we talked about MapReduce. It's basically a programming paradigm, and it helps us solve the big data problems, specifically sorting intensive job, and have two functions basically maps and reduces, mapper and reducer. That's the code you write. All right. So now let me demonstrate to you how does it work. Okay. Let's go step by step. Imagine that this is your function. This is your map function. Okay. Let me increase the font. So although it looks like Python, but I've tend to write it in a very pseudo language. This is your function. This is something you write saying this is my map function. It will receive an input for input data, and for each input it's going through word by word and printing word as the key and one as the value. Okay, as I told you that your map function will receive input. Okay, and this input has to be converted into key value pairs. So that's what your this function is doing. Okay, you could have done other things as well. You could have said here, you could have put something like concatenate something. Okay, based on what is it that you want to sort your data upon. Okay, now let's have a look at it. So your map function, this is our very small file. This is our very small file. On top of this file, we are running this map function. It's converting this data into key value pairs. All right. So sa re ga became savan, raven, savan again, gavan again. Okay. Now this dashed line you see in the diagram is something which Hadoop will do for you. It will take the output of your map function, sort it by the key you have provided, okay, and combine the values together. You can imagine that it's a big array of values. It's not really much, it's just all the values are brought together like a big array. All right, so you have got key and you have got value, and and this dash line shows that this key value is converted into ordered, it's sorted, and it's grouped. All the values for each key is grouped. So sa has got two values, 1 and 1, and here we go. Okay, so that's the duty of MapReduce. This dash line is the job of Hadoop. The whole Hadoop is to convert the output of MapReduce into this. All right, now the this data for each key value, the here ga is one key and values is only one, which is one, is fed to reducer one at a time. Okay, this is your function called reducer, and basically it looks like this. Okay, it could be, you see this function. So here, for each key value, your reduce function is being executed and it's being given the word an array. All right, this is an array of word, array of frequency. Now, inside this, you can do anything you want. Here we are just computing average. You might do, here we are just computing sum. You might do average, or you might do something like root mean square value. Okay, or any other magic you want. Okay, or you just return the minimum value or maximum value. So whatever you wish to do in the reduce function, it is absolutely up to you. Okay, so these two functions, the map function and reduce function, is your duty, and rest of the things will be taken care of by Hadoop. Okay, so, which one, Harshal? Is this intermediate step between mapper and reducer? Yeah. So this intermediate step, this sorting and grouping, is the magic being done by Hadoop for you. Okay. The dotted line represents the work done by Hadoop. All right. The sorting line. Okay. Yeah, it looks like MongoDB. I've just written this mapper reducer code so that it becomes very easy. If I try to write it in Java, most of the people will get intimidated. That's the reason I have avoided it that way. Okay, so here you get the word count easily. Okay, here you get the word count easily. All right, now moving ahead. Yeah, creating array is also done by Hadoop for you. That's correct, Sweta. All right. Now that was a very simple diagram where there was only being done on one machine. Correct. Correct. Thank you, Vinay. Basically, a conversion of list key one value into key and list of values, right? And here there is a list also. Okay. Yeah. Let me make it little more. All right. Awesome. Yeah. Now, that was a diagram where we did it only on one machine. I want to show you what happens in case of there are multiple machines containing parts of the file. Here, there is one machine containing this big data against which our map function is being executed, and map function read this file. Hadoop read this file, fed it to map function. Map function converted the file into a word key value pair, and then Hadoop took this output, sorted it, and given it to you. Okay, so most of the heavy lifting is done by Hadoop for you. You only had to write these two functions, that's all. All right. Now, what happens? How does Hadoop do in case of there are multiple files? So imagine that you multiple nodes. You have two nodes, node 1 and node 2. Node 1 contains one block of data. Node 2 contains another block of data. And against this block of data, we run the map function. And this map function converts this data into key value pair. On each node, we will be sorting the key value pair independently here also, and you can see in the diagram we have Sare Saga on one here. Then our map function converted it to this. Similar thing happened on the second node also. We have Sare Sa here, and then after the sorting has been done, we get this data, right? After the sorting has finished on both the nodes, and this data is then merged. This data, both data from both sides, the key value pairs are merged together, and then key and values is prepared like this. And then each key value is passed through your reduce function. Okay, so internally it can execute your work on one node, multiple nodes, or thousands of nodes. All right, is it clear, or have I completely got disconnected from you? Okay, so on each node, node 1 and node 2. Good, good. So on each node, node 1 and node 2, we will run it will automatically run the same code, whatever code you have written for map function here as well as here, and then whatever is the output, it will sort it and merge it. So these colored blocks is what is done by Hadoop for you. Okay. Now let me answer Harshal's question. So, is merge and reducers are running on the same node, and does this guided by the task tracker? Very good point. So, it is actually guided by the task tracker. So, generally, the map and reduce both maps will run on one machine, and reducer might run on either of these machines or maybe the third machine based on the load at that point of time. If this machine on which the reducer is running may be very basically the idea is task tracker will run mapper and reducer on the machines which are fairly free. Okay, if if the reducer is on the same node, in one of the node we save a little bit of transport cost. Okay, but that is just a one form of optimization which Hadoop tries to do. Okay, so is everyone with me? All right. Now, Nitika's question is, if there are, if I'm having 10 input files, will there be 10 nodes? Good question. Now, let me try to answer this question now. So, basically, the idea is that maps should run on each individual node where the data is. This map function will be executed very close to the data, so that lots of cleansing of the data and there is no transport cost involved between node and the map function. Okay, so if you have a big file containing 20 blocks, then the map function will be executed on 20 nodes. Similarly, if you have very small files, say 1 MB each, and you have thousand of such files, then again it will have a tendency to run on all those machines containing containing the data. So your data might be spread across thousands of machines. So although each individual machine will be fairly free, and and the data transportation will be little bit of more headache. Therefore, when you have small files, you tend to combine them together and keep it as a single file. All right, we'll talk about how to combine a little bit later. All right, if some of the map tasks are finished and not all, then reduce task starts running in parallel? Very good question. To minimize map task to minimize times. Uh, if some of the map tasks are finished and not all, then will the reduced task start running in parallel? Yes. So un- so reduced task does not start until all keys are collected. All values for a key are collected. All right. Therefore, therefore, reduced task will wait for all maps to finish. Okay. This can be optimized by something called we will talk about something called combiner. We'll talk about combiner which can start combining the partial data, right? Very good point. Now let me try to answer Nitika's question. Then I have to write map function twice if there are two nodes? No. The same code is cloned to exact same code is replicated to both the nodes and executed at both the places. Okay, identical copy. All right. If you have 1,000 nodes, then the copy of your map function will be made to 1,000 nodes. Okay. Next is what if you want to execute multiple reduce phases? It looks like this, but it'll be more clear if we show you the previous diagram. Okay. So basically, no matter how many reduces are there, okay, yes, you can definitely implement it practically. Yeah, soon enough, don't worry. Okay. All right. So the next diagram shows you that after sorting, there is a phase called merge and shuffle in which the data is being reduced on multiple nodes. Okay. In this way, no matter how many reduce phases are there, then no matter how many reduces are there, you will always have all the values for a key on a single node. All right. So that is one thing. Okay. Now the other way to think about what we did at MapReduce is it's a grand, it's a big, the grand way of saying group by. Okay. If you remember, group by has two parts. One is defining how to group your data, on what basis the data needs to be grouped. And the second one is how to group the data. Okay. So you define select word comma count star from table group by word. So what is it that you are doing? Here you are saying group by word, which is essentially saying that the way we said using MapReduce is my word is the key on which my data need to be grouped, right? And then count star is the aggregation. All right. Count star is the reduce function. All right. Sanjay's question is, does it always reduce in multiple node? No. By default, it reduces only on one node. You have to configure it to reduce on multiple nodes. It does not automatically detect that it requires more reduce phases. If you realize that combining the data is overloading your reducer and reducer is finishing really late, what you do is you start combining. You basically, if it's taking too much of time, then you say that I need these many reducers. That's all. Perfect. Yes, Harshal. Number of blocks is generally the directly proportional to the input mapper, the mappers. Okay. If your file is having 10 blocks, meaning if your file is how much? 1.2 GB, above 1.3 GB, you can say above 1.3 GB, then it is going to have 10 blocks. And those 10 blocks, if they are located on different computers, then there will be 10 different nodes involved in this process. Okay, the mappers will be run there. Sounds good to you? So blocks are on which basis? And that's Nitika's question. So if you remember, we talked about each file is broken down into blocks of 128 MB and is distributed across the cluster, right? So it's the same blocks we are talking about. So if your file is first, before you run MapReduce, you have to put your data onto HDFS, and then you have to use this. All right. Okay. So this analogy is clear to everyone. It took me some time to actually realize that MapReduce is nothing but a grand group by, or a newer way of saying group by, a more flexible group by. Here you can reduce in any way. In Mapper, the key on which you want to sort could be anything, not only a column, but anything. Here in group by, we generally group by on a column, but here you can group by on anything. Sanjay, are you with me in this? Sayed? Good. So Harshil's point is the only difference is in the DB temp table is created on the same node. Here it's distributed. Correct. So basically, on the DB, what we do is it's everything is being done on the same machine. So same machine is busy in doing stuff. All right. So all right. So in MapReduce, we exploited two things. It did two things for you. First, your data is anyway distributed. If you are dealing with terabytes of files, it's anyway would be there on HDFS, which means the data is already distributed, right? So when Hadoop is running MapReduce, it sends map to closer to the data, which means the data transport is reduced. Second, we have utilized multiple computers to solve our problem, and hence the overall speed is going to be really, really fast. Sounds good to you? Moving on. Now, these are few questions. I want all of you to go through these questions and come back tomorrow with the answers. All right? All right. So here you have to write the map reduce function the way we have written here. Here. Here the input was one line at a time. Here in the map function, the input was one line at a time. Okay. And here in the reduce, the input to your function was each key and the array of all the values for that key. Okay. Now let me just go through the all right, let me just go through the question. So my first question to you, all of you, is if you have frequency of letters, do you need map reduce? If you had to compute If you had to compute frequency of letters, do you need MapReduce? Okay. So don't answer now. Give your justification. And if you think that frequency of letters need to be computed using MapReduce, write the MapReduce pseudocode. Okay, just write the approach defining a function like the way we did here. Okay, so like here you will write break down input into one character at a time and then print out each character and one as the key value. I'm just giving a little bit of a hint. All right. Similarly, please write your reduce function like this. Plain English will also suffice. All right. So frequency of letters, you need to justify, do you need MapReduce? If so, how and why? Okay. Next is next is next question is little tricky. You are given a huge text, same text you can assume whatever we had earlier, and you have to find anagrams in the text. Anagrams are opposite of each other. Okay, anagrams is basically a different arrangement of letters in a word. Anagram does not need to have a meaning. All right. So if the input is this, if your file is totally this, so what I need is, if you see, cat, act, and tac are anagrams of each other. CAT, TAC, it's a different arrangement of characters in a word. Sounds good? So these three are anagrams, while the, to, and in do not have any anagram at all. All right. So how would you write MapReduce program to find out anagrams in a huge text? So is the problem statement clear to all of you? Feel free to ask. Is this input and output correlation is fitting to your psyche? Yes. So Ajay's question is, you would have to integrate with an online dictionary to find meaningful words. Do not worry about meaningful words. It does not mean right now here. So probably that will be a little more complex what Ajay is suggesting. All right. Now the next question to you is, there is a big file containing the DNA sequences of people. You have to find all the people who have the same DNA. Probably this will be the very, very simple question. For example, this is your input data. Each line is user ID and their DNA. Then another line, their DNA, another line, their DNA, and so on. Right? What you need to do is in the output, so user 1 and user 4, these two persons have the same DNA. You need to print their names, user IDs. User 2 does not have another, somebody who has the same DNA, while user 3 and user 5 have the same DNA. Okay, so this is what you need to print. All right, so what is the map reduce function you will get? In your map function, you will get each line at a time as the input. Okay, and rest is up to you. Now this third B is difficult. Given the DNA sequences of people, you have to find out all the people who belong to the same family. And the definition of family is the people in the same family either have exactly identical DNA or mirror image of the DNA. For example, user 1, user 2, and user 4 ACGT, user 2 TGCA, which is exactly opposite of ACGT, and user 4 is same. So either you have to bring all those users together who have exactly same DNA or mirror image of the DNA. Okay. So yeah, Ajay, I will tell you how to answer these questions. I'll show you the online place. Okay. So is this question clear? The difference between the previous one and this one? In the previous one, you had to bring those users together whose DNA was identical. Here, all those users you have to bring together whose DNA is either identical or mirror image, right? Is everyone with me on this? Any doubts on this? Good, good. Now, fourth question is a little lengthy. In an unusual democracy where everyone is not equal, the vote count is a function of the worth of each individual person. So, Nitika, a pseudocode will do. A pseudocode will be sufficient. You don't have to write in detail. All right. So all of you, basically, the crux of all these problems is figuring out what is the key in your map reduce and how your in your mapper you need to figure out what is the key, and in the reducer you need to figure out how to combine the values together. All right. Now, in this unusual democracy, people are not equal. Like in our usual democracy, we just count the votes and that's it. Here, while counting the votes, we are also checking people's bank account. Whosoever is richer, we add the proportional votes. Okay. So we are given two lists, voter and votee. And second list is person and its worth. Now, the so A voted to C, B voted to C, and C voted F. A's worth is 5, B's worth is 1, and C's worth is 11. Okay? So since A was voted by A and B, so the worth of A becomes 5 plus 1. That is, sorry, worth of C becomes a worth of A plus worth of B. And what is worth of A? 5. And worth of B is 1. Okay. So the worth of C is summation of all those people who voted for C, and that is A plus B, which is 5 plus 1. And hence C's vote count is 6. All right. Next is C voted for F and C's worth is 11. Therefore, F gets 11. While nobody has voted for A and B, and hence A and B's vote count is 0. So is the problem statement clear? You are given two lists, list 1 and list 2. Okay? And what is it that we are expecting out of it is this. All right? So before we think about this problem, I would like to tell you a few more things. So when we tell Hadoop, we give the following inputs. Okay, we give the following inputs. First is, what is my map function? Okay, what is my map function? What is my reduce function? My input files. Whatever input files, a list of input files we give to MapReduce, it takes all of those, combine them together, and parts by parts, it feeds to your map function. Okay, here you can imagine that you will get line by line as input. Okay, so is the problem statement clear? You are given two lists, list 1 and list 2. List 1 contains who voted for who, and list 2 contains the worth of each individual voter. And what we are looking for, the summation of the worth of all the people who voted for a person, and that's what is the result we are expecting. Okay, so basically, the other thing you might have to think about is it would require multiple passes of MapReduce. You finish one MapReduce phase, and in the next phase, again you in, make the output of the previous one as the input of the next phase. Okay, you have to create maybe two, three map functions, two, three MapReduce combinations. All right. So, is the problem statement clear to all of us? And do you by any chance realize, can anybody tell me what exactly was the real problem from which I have taken an inspiration for this problem? And as a hint, that was the first problem which Google tried to solve using MapReduce. Anyone? Okay. Uh, So there's an algorithm of Google called PageRank. On the basis of it ranks the pages, where one page is voting to another page, and the worth of each individual page is taken into the account. All right. So the PageRank algorithm somewhat works like this, but it's far more complex. All right. Good. So you think about these problems, and we will discuss it tomorrow again. Before that, I would like to continue with the session number 3. Okay. And okay, I forgot one thing, one discussion. So you should go to the website here, nobigdata.com, and if you click on my courses, you will see your courses. Here you see many courses because I am allowed for all the courses. Under under my courses, you will see session 1, session 2, session 3, and so on. And under each session, you will see the previous recordings of the session. Okay. The session which have completed will have your recording. The session 3, for example, will have the recordings of previous batch. Okay. And here, y- i- under each one, you will see the quiz you need to finish, and also presentation is available there. Installation instruction is available here as well as here. Also, the subjective question which we have talked today are also located. You have to answer here. You have to write your answers here. Okay. You click on assignment here, and it will open up the question like this, and then you can leave it blank or go to the next one. Okay. And once you have done, you can actually click on user account and see my results. Okay, and it will show you that what are the various quizzes you have taken and what all is in progress. Okay, sounds good. This is where you have to answer, and we will be giving the marks here. We have marked the number of marks for each question. Okay. Oh, the marks is not available in this. All right. I think I should display the marks allocated for each one. Let me take a note of it. All right. So basically, you have to write your answer here. That's all in the plain, in the pseudocode. Okay. All right. Now moving on to session number 3, which was supposed to be today. But initially, generally, the sessions are slow because we have more and more questions. So you don't have to, yeah, ignore that open ID in the login. Okay. You don't put anything in there. Don't put anything. You just log in with your username, which is provided to you. The idea was to integrate with your Google and Facebook account, and that is taking a bit of time for us. All right. Great. Now let's talk about. All right. So. All right. So we will discuss these problems tomorrow. Till then, you try to work on this, and let me explain something called a streaming job. Okay. So a streaming job is, so we just saw that we have to write MapReduce code, right? Where the MapReduce, ideally in the beginning when Hadoop was written, and Hadoop was written in Java, and so you could only write MapReduce only in Java. But streaming job, the MapReduce streaming job makes it possible to write to write the mapper and reducer using any program possible. Okay. All right. And this is how it looks like. So we'll start with this. So here you can see that I'll go step by step. So let's have a look at what is this folder. Okay. So here this is basically Hadoop command, and you are telling as the first argument that you are planning to execute jar. Okay. And then you provide the Hadoop library. Hadoop guys, they themselves wrote this streaming library, which internally contains basically the Java MapReduce. And then it expects these arguments. First argument is the input folder or input file. Second is the output file, and the mapper definition and reducer definition. And you can see that here we are providing the commands that need to be executed as mapper and reducer. All right. So Hadoop streaming job makes it possible to use any binary or any program as your mapper and reducer. The only thing is, the only thing is, your mapper is supposed to provide key and the values, and the only way to separate them is by tab. Okay. If you if your mapper outputs the data one line at a time, where key and value is separated by a tab, that's good enough for Hadoop. So Hadoop streaming expects your mapper program to give out key values separated by tab. Okay. And reducer will get the input which is sorted, not grouped. Okay, only sorted input you will get in the reducer. You will not get the data grouped the way you got it in case of Java. All right, those are the minor differences. All right, let's have a look at it. So Sare Saga will basically, this is our mapper. So who can tell me the meaning of this command? What does this command do? Anybody quickly? It replaces what with what? If space with new line. Excellent. Excellent. So basically, your mapper is doing nothing but converting the input file into one word at a time. Okay? That's all your mapper is doing. And this command will be counting the words. Okay? Let me again go through this. So imagine that this is your input file. Your SED command will be executed against this input file, meaning the output of your mapper, this is your mapper, right? This is your mapper. The output of the mapper would be this. And as we talked about, the key and the values should be separated by tab. And if there is no tab, the value is considered as null. Okay, value is just considered as null. And the data will be ordered by the key, which is the word itself, and you will get this dashed line is the job being done by Hadoop, and this is what you get as the end result of Hadoop. And being fed, this is what will be fed to your reducer. This is your reducer. All right. So you will notice that here the big difference between Hadoop streaming and Hadoop streaming and Java MapReduce is that in case of Java MapReduce, you get the values grouped together for a key. In Reducer, you will get all the values for a key grouped together, but in case of a normal reduce, you get the you get only the sorted values. Okay, and unique minus c will only count on unique minus c only works when the input is already ordered. If the input is not ordered, unique minus c does not give any sensible result. Okay, is this diagram clear to you? If it's not clear, you can ask me. I can explain each steps more in more detail. All right. Okay, in SED command, the slash g is global. It does not stop at replacing only once. Good. Thank you, Nitika. All right. And similarly, in case of the reducers are more than one, the data is sorted and the keys are all right. Let me go back. All right. Let me break down this. So here we are saying this SED command, if you have a look, what is it? What does this SED command say? Okay. So SED command here says replace. S means substitute this with this. Okay. Here this means space and this means new line. And do it globally for the whole file, whole input provided to you. Sounds good? Okay. So I'll show you. Yeah. I think I should be a little more. Okay, let me show you step by step. That will make it more clear. So let's say we have echo Sandeep Giri. All right. If we say SED substitute space with a new line, okay, you can see that. Yeah. So, Nitika, the only way we are just enforcing that with the absolute location of the unique command. Okay. We are providing the absolute location of the unique command. Okay. Now here, now let me just show you some more things. Okay. Sandeep Giri and again Sandeep. All right. Now, if you run unique, so whatever the output we got just now is the result of substitution of space with a new line. If we do not do this, if we do not pass, so you can see this, okay? So echo generally prints everything onto the screen. Now we are passing the output of echo to SED. We get this, all right? And in case we give the output of this to unique, we get wrong result. You can see the wrong result. It's saying Sandeep has come once, Giri has come once, Sandeep has come once. Reason is the unique expects the data to be sorted. So if you use a command called sort, then you get the desired output. Alright? And this sort command is what is the duty of your Hadoop. Okay? Hadoop streaming is what is doing this sorting. Rest is same for all of us. All right. Now here we go. Similarly, if you have more than one reducer, the key output of this after sorting is spread across multiple reducers, making sure the key is always one key is always on one machine. Yes, you can use the same logic. You can think about breaking down a word into characters, and that can be done using Unix commands. All right. Now let's try to run this command. Okay. So let me open this up. So all right. So this is our usual Hadoop streaming command. This is the folder that contains our file. Let's have a look at this folder. Okay. So we say Hadoop fs minus ls and the folder name. So it has something called big.txt. It has something called big.txt. We say Hadoop fs minus cat this. Ouch, it is going to take a lot of time. So it's a big text file containing the data. You can also have a look from the hue about this folder. Okay. So it's going to take a little bit of time for me. And also check if this folder already exists, and these are the mappers and so on. Okay. And since they are in the multi-line, let me just put a backslash. Otherwise, I'll have to put everything in a single line. Or let me just make it a single line. All right. I'm just putting everything in a single line. You can see that. It's stuck. All right. Now, so I'm launching this. So it says the output folder already exists. Okay. And you have to either delete the folder or specify other folder. Okay. So let me just run it again. The same command, it just I've converted it into a single line. The location of the input files is in the sgiri/word count/input. Sgiri is a relative folder with respect to your home folder. Yeah. You can go to the web here. That will probably give you a better idea. So yes, this jar file comes with your Hadoop installation. Okay. This file, the jar is nothing but a big bundle of Java code, Java compiled code of Java. And this bundle comes with, this big bundle comes with Java itself. Okay. Now let's have a look at, okay. So here the MapReduce process has begun and the output folder has been created. The output of the data is here. Okay. Let's see. Hadoop fs minus cat. Yes, big.txt is our input input file. So under sgiri, which is a relative folder from home, so before that, I think I will show you in Hue. Okay, so under output folder, you see these files. Do you see these files? So these are this is what is generated. These part files, if you have multiple reducers, you will have multiple files. Since we had only one reducer, therefore there is only one file, right? So let's have a look at what is there inside this file which is just generated, and we can say Hadoop fs minus cat this file, and we can say more. Correct? You can see the counts. Yes, it is we who decide how many reducers there should be. All right. So where is asgiri here? Asgiri word count. Let me just go to Asgiri. Yeah. Is the voice breaking for everyone? Hello? All right. So this is the output. This is the output generated by our MapReduce. Okay. Okay, the voice is breaking. Let me try to do. All right. All right. Is it audible now? Hello. Hello. Yes. Ouch. Hello. All right. So I guess the voice is heavily breaking. It's audible now. All right. So I was showing you the where is the file located. So in this ASCII word count and input is the folder where is our data located. Here you can see under word count we have not word count, it is word count. All right. Here you can see that there is an input folder here, and you see this big.txt. This is our input data. This is what we gave to our command as input, and this is our output folder. This is what it generated as the result. So do you want to make it better? Do you see this is our word count result? Double quote, single quote, come has come once, double quote, single quote, and so on. And you see, do you want to make it better? Are you happy with this kind of word count program? What is it that you would like to improve here? Okay, one is short. What else? Without the special characters. Okay, so okay, so where will you exclude those special characters, in map or the reduce? All right, in the map. All right, so let's make that command a little better. Vinay, are you able to hear now? All right, I'm just hoping that now this does not break. The 4G seems to work now. All right, so here is some more changes I have made. I'll go step by step here. Okay, so in the mapper, this time what I'm doing is after first I'm replacing space or tab any number of times with a new line. Okay, so the definition of space is spaces, meaning white space, or a tab any number of times. Okay, this is what it is. So how many of you have actually gone through the first video here? It basically goes through a regular expression session. Okay, make sure that you finish this regular expression session. Okay, so you have to replace space and tab with a new line, and whatever is the result there, I'm trying to substitute again anything which is not alphanumeric with nothing, and then translate capitals to lower. Okay, so basically I'm trying to remove special characters, non-alphanumeric one, and then convert everything to lower casing using a shell command. You can do the same thing from using Python, provided in your map function. You can do using any program as long as your program reads from standard input and writes to standard output. And the way your program has to differentiate between key and value is by the way of tabs. Okay, now the problem here is, since our mapper is now more than one command pipelined, now we cannot use it just like that from the command line. So what we need to do is we need to create a separate file. So we'll create a separate file called mycmd.sh, and we'll write this program in that. Okay, so let me just remove this double quote here. This rest is good. Okay, so after we have written it into a file, we will just provide the reference of that file here and here, and then we can execute it the way we want. All right. So we have my CMD here already created. I hope you can see it. We have already created this. So all we need to do is we need to provide, this is our standard jar file, then this is our input folder. Input folder remains same, while mapper, our definition of mapper is now my cmd.sh, because my cmd.sh is the one where we have put all this new command, and reducer remains same as the previous one. What was the reducer earlier? If you guys remember, any of you remember? Reducer will remain same as this one. Okay. Now there is one more thing here. Notice this. Okay. So what is it that we are missing? Yeah, it requires one more folder called output, and output is into asgiri word count, and then output, and let's call it 18 April. All right. Now, whenever in case you are giving a program which is not existing on all the nodes, you need to ship it. And the way you ship it, by providing an argument called minus file or minus files. Okay, this way the Hadoop will take whatever files you are providing, copy them to the destination uh, at every node where mapper is going to run, and it will execute it then and there. Because these mymapper.python or my cmd.sh does not exist on the target machine. Therefore, Hadoop needs to first copy them. Earlier, those commands which we use like sed and unique, they were existing on all the nodes. That is why Hadoop ran it without complaining. Okay, so it has now generated this output folder. It says output folder is there. Now you can see, all right, what is inside it. Let's have a look at it, or we can actually go to our web page, that is easier to see. Okay, so this time it is far more cleaner. Do you see it's far more cleaner? All right, now let me just go to, say, last block. So here is this. If I want to see it in a sorted way, what can I do is I can pass it through my sort command, and I can say to my sort command nr, numerically and in a reverse order. Now you can see the is the most common word in this, which means it's definitely an English language. Okay, and you can see other words also, right? All right. So that way you can execute all of any program as mapper and reducer. Okay, whether you are writing in Python script or shell script, the only thing you have to take care of is whatever program you are writing or using, it should take input from standard input and give output to standard output, and later on, and while your mapper need to give the key values separated by a tab. All right. Also, you can try one more thing here. You can specify number of reduced tasks. Okay. So while we were running it, you can run it like this. Okay. So you have to provide here the argument like this. Ouch. Oh, I think I have already written it somewhere. Let me copy it properly and then I can do it. All right, do you see this? And just a second. So all you need to do is something of this sort. Right. So basically you have to provide that as the first argument just after jar. It should give an error ideally. Okay, it should not give an error. All right. Whenever you are starting any MapReduce job, it always gives you a URL to track where you can see the progress. Also, in case you are writing your Java program or anything, those results will also be logged like sysout, syserror. All of those things will get logged into the log file provided by this interface. Okay. So Vikas's question is this MapReduce alternative to what we did earlier using MapReduce, meaning we do not need to write MapReduce programs. So we are still writing MapReduce programs. It's just that we are providing in the form of any binary or scripts. Okay. So here is my output folder. Okay. Also, this is the detailed statistics of what went on, how much data was read and how much data was written. Okay, so we are still writing the scripts, and so here if you see, these are the mapper and reducer programs. Okay, we are still writing mapper and reducer programs, just that we are not writing it in Java. Okay, if in the traditional way in Hadoop, traditional way you have to write MapReduce in Java. Using streaming, you are able to utilize any script or any program as mapper and reducer. Make sense to you now? So now let's have a look at what is going on here. So am I doing something wrong? Word count output 18 April dash 1. Output 18 April dash 1. You see, here, this time, since we provided our command with the MapReduce task equals to 2, it created two parts now, part 0 and part 1. Okay? So part 0 contains one part of the data and part 1 contains another part of data. So internally, some keys are partitioned and went to one file, other keys are partitioned and went to another file. Okay? And how these keys are partitioned can be defined by you using a partitioner program. All right. Now, to get the full list of Hadoop command, you can actually, the best way is to go to command line and say Hadoop. It will show you all of this. And then you say Hadoop FS and it will show you the detailed commands here. Okay. And you can say Hadoop -fs help on say RM. So shows you the detailed help on RM or help ls. So you get the detailed help on ls. All right. So great. So we were able to run our streaming job on using multiple reducers, as well as we were able to utilize the Unix shell commands as our program. Okay. You can use Python, you can use PHP, you can use any program that can execute on Unix machine as your input. Okay. All right. Did not understand the task equals to. So if you see this diagram here, there are three reducers, right? If you want to tell Hadoop that, hey, I want three reducers, you can tell that by the way of specifying this argument. Okay. You can say 3 here. If you want 3 reducers, you can say 3 here. Okay. Yes. So Vikas's question is there any benefit? Right now there is not much of a benefit in case your reducer is taking too much time. So every time you finish your job, you should review this part. Okay. How much time your reducer is taking. It shows you the detail total time spent in reduces in occupied slots. Okay. Total time spent by all reduced tasks. So this is the number you need to look at. In case this number is too much, that means your task is taking your reduced tasks is heavily overloaded. You should break it down into two or more. Okay. So if your reducer is overloaded, if there is a single reducer, you should generally break it down into multi reducers and so on. Okay. So two output files are due to two reducers. Each reducer saves its data into the output. Let me go back to our session number 2. There we had this nice diagram. Okay. So this diagram will make it a little more clear. So there was one part on which we ran our mapper. It gave the results, put it in two buckets. Similarly, there was another part. It gave the results. Mapper gave a key value pair and sorted the results here and put it in these buckets. These buckets are carried over to two different machines. These are the two parts you see, part 0 and part 1. What about mapping in different nodes? Meaning, so this is where the mapping is going on. So total number of mapper is a function of how many blocks does your file has. Okay. Yeah, so let me have a look at how many splitters we had. So this basically launched two map tasks. Looks like our file has got two map tasks. Okay. All right. Will it be equal to the number of blocks or number of inputs in input split? So input split is a representation of input block. Okay, generally, but the number of mappers is a function of how many input splits are there. Okay, and generally we try to keep number of input splits equal to number of blocks. We will talk about what is an input split and how it is created on top of a block a little later, but just for those curious people, input split is created on top of a block. An input split is a meaningful representation of the data. Input block, the block in HDFS is a raw data, while input split is something like line by line data or maybe a CSV file or key value files. Okay, make sense, Mishra? Vikash? All right. So should we move on now? All right. Next point is that also have a look at this page. It tells you in detail, as in what is expected out of MapReduce. Also, in case of the complex keys, in case you want your keys to be sorted by numerically, okay, so you can specify that in argument. Similarly, if you do not want reduce, you can specify that you do not want reduce, and so on. So have a look at this once you get a little bit free time. If you want to get more details on, say, you want to have a special way of sorting your keys, okay, you can specify that here. So you can customize this Hadoop streaming to a very large extent and control it. All right, we have already done hands-on. Now there are few notes I want to discuss with you. First, it is okay to have no reducer. There are cases where you do not want to group the data, you don't want to do anything after sorting. All you want is whatever is the output, I want to save it as such. It is okay to have no reducer. In case, all right, so you can say Hadoop jar, blah blah blah, and then we may skip the reducer absolutely. We have specified, yeah. So we have specified the mapper, but we have not specified the reducer here. Okay. In case you do not want Hadoop to sort your keys, if there is no need, say you are just translating data from one form to another, you have no inclination right now to sort the data. You can tell that that there are no reduced tasks. Okay, there are no reduced tasks. By saying minus d map reduced task equals 0, and there will be no sorting of the data. And maps will decide number of output files. Number of mappers will decide how many parts are going to be in the output folder instead of reduces. All right. Now you may ask, like, how many maps are there? We've already discussed. Number of maps is a function of number of input splits. You can also force Hadoop to have number of maps of your choice. If you want more map tasks, you can say you can set in the config the number of map tasks. All right, few more notes. Now, since this number of reducers is up to you, you may ask that how many reducers are ideal? Should I choose one? Should I choose two? Or how many reducers should I choose? Okay, meaning on how many machines I should run my reduce tasks. All right, so the good number is somewhere between 0.95 to 1.75 multiplied by maximum number of tasks possible. What is maximum number of tasks possible? How many tasks can be executed simultaneously on each machine, which is 2 by default, and multiplied by total number of machines available to you. If you have 10 machines, then maximum number of tasks that can be executed simultaneously is 10 into 2, because by default we are saying you can execute two tasks parallelly on one machine. Okay, so the magic number of how many reducers, in case you have 10 nodes, max task is 20, and therefore the number will be somewhere between this multiplied by 20. So somewhere between 19 to 35. Okay, it's a huge range, so generally you do a little bit of trial and error. So if you have more number of reducers, it will be faster, framework load might increase, and it lowers the chances of failure. All right, are you with me? Yeah, it's an empirical number. So yeah, first point is that, okay, so there is something called maximum reduced tasks that can execute simultaneously on each machine. Okay, Na- maximum task that can execute it per machine simultaneously. By default, that is 2. If you have 10 nodes, so total number of tasks you can execute on machine is 20. All right, so the total number of optimum reduces is between 0.95 to 1.7 times the maximum tasks possible. Okay, that is an empirical number which the people who have done a little bit of experimentation of MapReduce, they have come up with this number. All right. So is the voice gone for everyone? All right. All right. So yeah, should I explain again, Sanjay? So 0.95 to 1.75 times the maximum task possible. This is the thumb rule to create the number of reducers. If you create 0.95 into max tasks, then the framework load will be lesser. Ouch. I know, I know. Yeah. Hello? 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 I think the audio is not yet clear. Ouch. Today is the most horrible day for me. Alright. So I must have three replication factor for the internet. Yeah. O- Okay. So, alright. So is this clear? How many reduces should you have? Should we explain again? Not clear? All right. So generally there is a confusion. Should we have one reduced task or multiple reduced tasks? Okay. So general thumb rule is a factor a factor multiplied by total number of reduced tasks possible. Okay. So if each node can execute two tasks parallelly or simultaneously, multiply that with total number of nodes, that becomes 2n, what if you have n number of nodes, and then multiply it by somewhere between 0.95 to 1.75. Okay, that's an arbitrary or maybe empirical number the Hadoop guys came up with. Okay, so if you have a factor of 0.95, that means less reducers. If you have 1.75 times the max tasks, that means more reducers, and means the overall work of reducers may be faster, more framework load, and lower chances of failure. Why lower chances of failure? Because you have more map reduced tasks defined, and therefore the in case some of the tasks are going down, other can take the load. Okay. Yeah, so we generally pick something in that range. All right. But most of it is arbitrary. If you are running some task every day, you should try running with multiple number of reducers and then figure it out. All right. The general thumb rule is, if your reducer is doing too much of work, then have more reducers. If your reducer is doing nothing, it's just passing through, then there is no need of having multiple reducers. All right. All right. Moving on. So we will talk about these. Yeah. Now there are few limitations to MapReduce. Okay. There are few limitations to MapReduce. If your job can be very well done on a single machine, and in future, if there is not much of a data you require, then do, don't don't do it using Hadoop. If it can be very well done on local machine on a one node, don't use the MapReduce. Second is, if your computation depends on previously computed values, such as Fibonacci series, you do not need MapReduce. There is no point in using MapReduce on that. Okay. I- Other is, if you have real-time response requirement, then do not use MapReduce. Okay, because the way MapReduce has been designed bottom up is for batch-wise processing. Okay, and in case your algorithm continuously need a central state, then we do not need to use MapReduce. All right. So that's pretty much for today. If you have any questions, we will talk now, and then we can call it a day. Yeah. So do you have any questions, Nitika, other than how much left? All right. So work upon all those problems, those four problems we talked about. Basically, those are five problems. Okay. Work upon those, and those are available somewhere here. All right. So please work upon this. I would say that i- whatever time you have, you should just try to answer these questions, and we'll have the detailed discussion on these four problems tomorrow. Okay. All right. All right. I'm extremely sorry for the bad internet connection today. Yes, we will. Yes, I'll tell you tomorrow. We will discuss how to write Java programs, uh, i- Java MapReduce tomorrow. All right. For time being, you can try to write in pseudo language, and then you update your code here in Java or Python or whatever language you want to do. Okay. All right. All right. Then see you tomorrow and have a great day. Okay. And please provide your three slots. I have got only emails from 2 to 3 persons, and yeah, please send that details right away. Okay. All right. Good night all. Bye bye. Not to all, because some people are in the morning. Bye bye. Have a good day.